let's go back to our discussion on generation. Right? Generation is the fourth technical challenge, focusing on taking in some latent variable or some small amount of multimodal data and generating more multimodal data. And the whole idea is to learn this generative process that when you create multimodal data, it still respects some constraints. It respects the interactions between one modality and the others. It respects structure within its own modality and should be coherent within each modality. We looked at three big case studies. Summarization, we take in more data than you have, such as a very long video, and summarize the most important parts, such as one image or one particular sentence. We looked at translation, where the idea is to take in data from one modality and maintain the interactions as you generate data corresponding to another modality. So it's taking an image and generating its caption describing the image. And finally, creation, taking in something smaller, such as latent variable, or maybe one image and generating more data, generating other images that may be coherently following that image, or generating text descriptions that might be long in nature, or generating audio that might be long in nature. So again, going from something small to something larger while respecting these constraints. That's increasing information content. And we also saw at a high level that despite these individual case studies, there's two important dimensions of generation. One is how the information content changes. And when we talk about information content, the underlying key idea is that how do these modality interconnections change as we have to summarize, keep, or increase our data. So recall modality connections are the relationships between individual elements across multiple modalities. And there's many dimensions of these interconnections, right? From a statistical point of view, they can be associated with each other due to correlation or co-occurrence. And from a semantic point of view, you know that they are associated with each other because they correspond to the same underlying object and so on. So you have any type of interconnections within your data. So for example, let's say that's a multimodal data. There's some interconnections. Again, they might not be one-to-one. Some elements of some modalities may not even be connected to other elements of other modalities. What summarization does is look at the most salient interconnections, right? Looking at the interconnections that matter the most. And again, this can be interconnections, and it also can be parts of modalities that are not connected to other ones. So that's summarization. And the example that we saw is that if you had a very, very long video, for example, this very long instruction video, and this very long transcript for this instruction video, how can you summarize it into a very short one-sentence description? And within this one-sentence description, again, it's going to contain elements from the long transcript, elements from the long video, their interconnections, and also elements within the transcript and video that are not connected to each other. For example, the fact that a video describes a Cuban breakfast, and it's a free cooking video, although it is not referenced at all in your transcript. So again, taking these interconnections, looking at the most important ones, and summarizing them, and also accounting for the fact that the elements that you summarize may not be connected to the other elements. For translation, it's more about taking elements from one modality and translating it to the other modality while respecting these interconnections, right? You want to be able to translate from one to the other. And of course, if there's something in the first modality, the right triangle over there, that isn't connected to anything in the second modality, then there's no possible way for you to translate. And again, the example we saw is that you had these very cool examples. So you generated realistic images given some nonsensical text, an armchair in the shape of an avocado. So looking at the interconnections between every element in the text and being able to generate it compositionally within the image. That's translation. And finally, for creation, you're again taking smaller amounts of data and generating more data, right? You want to generate more data, but the data that you generate, for example, this part, should still maintain interconnections with the other modality that you generate at the same time. Right? So these modalities will respect these interconnections. And also at the same time, the modalities that you generate within, the elements that you generate within the same modality, so all your sequence of triangles, that should respect the structure and coherence within that modality. And likewise, the elements in circles that you generate should also respect structure and coherence. And creation is in general a very, very difficult problem. I don't think there's any successful work on it yet. But ideally, what you want to do is that you want to start with some latent variables, some factorized latent variables, or maybe some smaller modality, and really generate more data than you started with. So for example, being able to generate coherent images in a sequence, generating very long text that describes the image, and generating snippets of audio that also describes what's happening in the text and within the sequence of images. So again, the relationships between the modalities that you generate is all about respecting these cross-modal interactions. And the structure of your modality, the structure of the data that you generate within the same modality should respect temporal, causal, and logical structure within that modality. So again, all the aspects of representation and alignment to capture these interconnections, and all the aspects of reasoning to make sure it's temporally and causally coherent all comes together in creation. So that was information content, how information changes as we summarize, translate, or create more multimodal data. The other big dimension is the generative process itself. After accounting for these interconnections, you still need to have a process to actually generate high-dimensional raw data. And a key idea here is that you also want to respect the heterogeneity within that modality. You want to design methods that are able to generate realistic data, respecting the heterogeneity of each modality. And for this generation dimension, we have two general examples. One is exemplar-based, where you have a dictionary of translations, perhaps stored from your training data. And if you have a new thing that you want to generate, you can look it up in this dictionary and find the closest one and retrieve the output. Nowadays, people also typically use generative models, where you have a dictionary of translations, but you're learning this mapping from one modality to the other using a translation model that is parameterized. And once you've done that during training, you can then test it on new data by passing it through the translation model. So this typically allows you to interpolate more between the dictionary of translations that you have. The exemplar-based is typically more rigid. You're going to get better guarantees on what you can output, but you're also limited to the amount of examples that you have in your dictionary of translations. So again, that was a very quick overview of generation. Three things: summarization, translation, and creation, and two dimensions: how the information content changes as we maintain or increase these modality interconnections, and how do we actually do the generation through generative models. And we saw many critical examples of ethical concerns, right? You want to be able to generate these modalities, but you're going to be at risk of running into ethical concerns, especially because you're starting to generate data. For example, there are examples where you took a generative model and I tried to increase the resolution of an image, but ended up turning an image of a black person white. You have these language models that are also autoregressive generative models that when you train on large amounts of data have been shown to regurgitate sensitive information like phone numbers or addresses. And also cases like language models where after you train it, it captures spurious correlations between gender pronouns and occupations. But yeah, just to recap from last lecture. So we started off on our second dimension. So everything in the first dimensional interconnections we've already seen, right? That's all alignment, representation stuff. So the big key idea is the second dimension. How can you actually define a generative model to generate realistic data, given the fact that you've encoded and captured these interconnections? So the key idea in all of this second discussion is generative models, right? Instead of learning a classifier P of Y given X, you're going to try to learn a generative model, P of X, where X is any samples of data that you have, text, images, and so on. And ideally, this P of X should serve two purposes. Given some X, some input data, you should be able to evaluate how high the likelihood is, evaluate P of X. So realistic data should have high P of X and nonsense should have low P of X. And you should also be able to sample from P of X. So defining a parameterization of P of X, you should be able to sample new X according to the high density regions. That should correspond to realistic looking images, realistic looking sentences, and so on. And typically, when we talk about these generative models, when we have a P of X, there might be also an encoding objective that goes from X to a latent variable Z, and that can be very useful for unsupervised representation learning. So you saw our first big paradigm for generative models was that based on latent variables. We have data X that are observed, but the actual way they want to generate X is from some set of latent variables that are unobserved. For example, if you want to generate human faces, it might be conditioned on some latent variables such as the color of my eyes, the color of my hairs, the pose, and so on. So this set of disentangled latent variables is not observed. We want to learn them. And one general way for learning them is to first put a prior, Z, on these latent variables, and then define how we can actually get our likelihood of my data X given these latent variables. So that's P of X given Z. In its most flexible form, P of X given Z can be defined as a neural network, a Gaussian with parameters defined by neural networks. And as such, if you maximize the log likelihood of your data, P of X, ideally you want to learn latent variables that actually correspond to these meaningful latent variables of variation, right? The fact that you can distinguish between generating based on eye color or hair color and pose and so on. And one key idea between latent variable models is that although my P of X given Z is simple, that's just one Gaussian distribution with parameters given by a neural network, my actual P of X, which is the integral over all Z, P of X given Z, can be very expressive. There's sufficient number of dimensions of Z this actual P of X can be very expressive. It's going to be a very complicated mixture of these individual Gaussians, each P of X given Z. And finally, one very desirable property is that if I have a new image X, not only do I want to do P of X given Z, I should also be able to do P of Z given X. And that's the inference model. And this inference model is typically useful for representation learning because you can take this image X, go into latent variables. And typically many times your label space is defined on these latent variables, right? You may want to predict the pose or the eye color or hair color of this person's face. So going P of Z given X should also be possible for representation learning. And we saw a first example of these latent variable models in practice, which are these variational autoencoders, where again, Z's are your priors, Gaussians, and P of X given Z, the transformation from your latent variables to your data is given by neural networks. And if you have a data set of just X without your latent variable Z, a generic way for learning these Z's and parameters in the model is to maximize the log likelihood of your data observed under this latent variable model. So your log probability product over all data points in your data set, and for each data point, the likelihood of that data point under your generative model. The log product becomes sum of logs, and your log likelihood is actually decomposed as a function of summation across all Z's, marginalizing across all Z's, P of X and Z. And typically, if you have something simple for Z, the most simple case is the Gaussian mixture model, where Z just takes a categorical distribution across k possible numbers, then you can solve this exactly. Right? You can compute the log likelihood of your data from each cluster and sum over your k clusters. But in variational autoencoders, your Z's are dense neural network features of perhaps very high dimensions, and each dimension is continuous. So even in a case where Z is binary, this is going to be quite intractable. Your summation over Z, even if Z was small dimension, like 30 dimensions, and binary for each one, that's going to need you to sum over 2 to the power of 30 terms. And when Z is actually continuous, like in real world neural networks, then your integral is going to be very difficult to compute. And that's where we saw the first key idea of solving VAE. So you got to do some approximations. Right? You got to choose simpler distribution Q that can be used to approximate your true distribution P, because P is intractable to compute is log likelihood. And one notion for measuring how close my distribution Q is to my P is that of KL divergence, right? We want the Q that you choose to be simple enough that you can sample, you can compute expectations and so on, but also Q to be expressive enough so that it's actually close to P. And one measure for measuring this distance out is KL divergence. Define KL divergence between Q and P is defined as an integral over Q, so expectation over Q, and this log likelihood ratio of Q of Z over P of Z given X. And visually, it looks like this, right? My P is really complicated. A bunch of modes in the multimodal up and down. I care about fitting a Q that is simple, perhaps just a one but unimodal distribution that fits P exactly on the modes which Q covers, right? So if Q is low, for parts of P that Q doesn't cover, you're not computing any error because your integral over Q for Q being small is 0. So I only care about the parts where Q is large. So where Q actually has mass, it must overlap with where P's masses are. So interesting. So this KL divergence is an asymmetric function. In this case, we've chosen KL, Q, and P. You look at the other way, KL, P, and Q, then that doesn't really make sense because you're actually going to have to compute an expectation over the first distribution in your KL. So the actual expectation over P is difficult. We can't do that. That's why we do the Q in front. So starting with this KL, we derive the evidence lower bound. This KL term can be written as the actual log likelihood of my data under my simpler distribution Q. So however my simpler distribution Q explains my data, plus the log likelihood of my actual data minus the entropy of Q. That just follows by the definition of KL. We know for a fact that KL is non-negative, so this is greater than or equal to 0. You can rearrange the terms and get a lower bound on my actual log likelihood of my data. The log likelihood of my data is at least the likelihood that I observe my data given this simple distribution Q plus the entropy of Q. And we know that this is equal when Q and P are exactly the same, but in general it's not equal, right? We want to balance this trade-off. We want to look for a Q that is simple in nature that you can sample from while still being a very close lower bound to the actual log likelihood P. And typically what we can do is to define Q in terms of some parameters phi. For example, Q can be a neural network that takes in Z and outputs a distribution over Z. Now, across many settings of this parameter phi, some estimates of Q are going to be good, some estimates of Q are going to be bad. And how good and bad this estimate of Q is can be defined as the KL divergence between Q and P, right? So log P of X, that's my true log likelihood of my data. That's in blue, that's constant. This evidence lower bound is in this red dotted line that changes as I change my phi, my parameters for my Q, and the distance is the KL divergence. So that gives us a nice recipe for actually learning these autoencoders, right? You want to learn this encoder model that takes in X and give you Z, and you also want to learn the decoder models of going from Z to X. And essentially, if you write down some math, learning this autoencoder boils down to two terms: the reconstruction term, which is the first term that we saw in this evidence lower bound. How much can I actually explain my data given this simpler distribution Q? So this expectation over Q, the log likelihood of seeing my data, P of X given Z, and also a prior. That measures the KL divergence between my chosen distribution Q with some prior Z to ensure that Q is actually simple. And essentially what you can do is to take your data X, pass it through the encoder, that gives you my distribution over Z's, that's my Q of Z given X. And once I have data variable Z, you can then apply a decoder, P of X given Z, back in the data space. And you want to measure how similarly you can reconstruct your data while ensuring that the Z that you learn respects the prior. And so if you want to learn this all about computing the gradients, right? The gradient of the first term is easy. You've seen this from last lecture. You want to take gradient with respect to theta, which are the decoder parameters. That's easy because it doesn't depend on the KL term. And you can move the gradient with respect to theta inside the expectation with respect to Q and approximate that using samples. The hard part is computing the gradients of the encoder. And the main difficulty is the fact that we want to take a gradient with respect to phi, your encoder parameters, that is like expectation under Q of phi, right? So how do you move this gradient inside the expectation? And we saw that you can actually do this reparameterization trick. In general, if you want to take a gradient with respect to Z of an expectation under Z, and Z is some simple distribution that you can convert to a Gaussian. So instead of sampling Z directly from the Gaussian, you can sample first epsilon noise and transform it with the mean and variance parameter. So multiply by the variance at the mean. Then, given that the expectation is only under the noise, you can move the gradient with respect to phi inside the expectation under the noise. And once you move the gradient inside the expectation, you can convert the expectation to samples. Right? Expectation over your noise samples epsilon become a variance, become an average over the noise samples epsilon that you sample. So visually that looks like this, right? If I have my data X, my phi tells me the parameters of Q of phi. So typically that's a mean parameter based on a neural network and a variance parameter based on a neural network. X and phi together gives me my Z, from which I sample it. And afterwards I have Z, I go through the decoder to get my actual loss function, like my KL or my reconstruction objective. But if you sample Z in the middle, that gives you a bottleneck. You can't backpropagate a gradient through a sampling operator. Reparameter transform says that instead of having X and phi sampling Z, I'm going to first sample a noise vector epsilon. So that's going to be random. And given my sample noise vector, I can deterministically transform it based on the parameters phi, the mean and the variance. And together with X, that gives me my Z, my latent variable. So now if I want to use my Z and compute some loss, I can backpropagate the loss through Z and to the parameters phi, bypassing the stochastic node. So that gives us a recipe for learning our VAEs, right? First, if you have data X, pass it through the encoder, where encoder is defined using our parameters mu and sigma. That tells you that is your neural network to learn the parameters of my latent distribution. That gives you my Q of Z given X. In the backpropagation step, I'm going to first sample epsilon noise vector and compute my Z given this epsilon noise vector. So multiplying it by sigma and adding my mean. And then I can compute the actual likelihood of my data, the log likelihood of my data, P of X, given this sample Z vector. So any questions about VAE so far? Yeah, good question. So typically, so encoder decoder structures are quite broad, right? VAE is a special case where it's stochastic. We actually have to sample the Z and you're learning it by variational inference. In general, encoder decoder structures, they can also be deterministic. And if they're deterministic, you can learn it by MLE, right? So taking an X, just going to a Z without any sampling and going from Z back to whatever decoder that you want to output. So if it's fully deterministic, you're going to learn those parameters using just maximum likelihood and stochastic gradient descent. VAEs just happen to be stochastic because you want to learn this latent distribution from which you can sample more data. So we parameterize this Q of Z given X as a Gaussian distribution, and that made it more difficult because you have to do the reparameterization trick. If you want to make it deterministic, then your Q of Z given X can also just be like, a categorical set of distributions, actual vectors, without the actual Gaussian continuous distribution. If it's just deterministic, then you don't have to do any of this sampling. The greatest pros and cons is that if you have a continuous latent distribution, they're also going to be able to interpolate across high density regions and low density regions. If you just have a deterministic model, then you're only going to observe some latent variables. It's not clear how you're going to interpolate between those samples as you want to generate more data. Does that make sense? Right. No, that's a good question. I'm going to get into that in about 2 slides. Any other questions? Cool. So just one connection I want to make. Some of you remember this slide from stochastic optimization. We talked about it in reinforcement learning, but both VAEs and reinforcement learning tend to solve this type of problem. It's a stochastic optimization problem where you're trying to maximize over some parameters phi that you want to learn with an expectation under a distribution that depends on phi and some objective function that depends on, for example, Z. So in VAEs, what we saw that you want to maximize the evidence lower bound, and the evidence lower bound can be seen as an maximization over some parameters phi, an expectation under my posterior distribution that tells me my latent variable Z given X, that depends on phi, and subsequently the log likelihood of my data. How likely I am to observe my data X given the Z. Right, so that falls under this broad class of stochastic optimization problems, right? The Z over here are my latent variables, the intermediate of my variational autoencoder. My Q of phi of Z, my distribution over my latent variable Z, depends on the encoder parameters phi. And my F of Z is the log likelihood of my data after I've obtained some Z. How likely the Z is able to reconstruct my data. So in general, we saw that we can solve this type of problems by reparameterization, right? We require that, first of all, Z is continuous. We can reparameterize Q of Z, but instead of having Q of Z as Z, sample from Q of Z, you first sample the noise vector epsilon, and then transform this random noise vector epsilon deterministically with respect to this parameters phi. And once you've done this transformation after the random sampling, you can then move the gradient with respect to phi inside the expectation, right? You solve that by reparameterization. And of course, your F of Z subsequently, after you sample Z, should be differentiable with respect to phi. And we have all of that in variational autoencoders, right? So therefore, what you could do is actually sample, instead of sampling Z, you sample the epsilon vector first and then transform the epsilon vector using my mean and variance parameters into Z. We also saw something similar in reinforcement learning. In reinforcement learning, you also try to maximize some parameters phi. Those are your policy parameters with respect to some reward, J of phi. So for each particular setting of your policy parameters, you can deploy a policy and look for its expected long-term reward in your environment. That's your reward. So writing it more explicitly, my reward is an expectation over trajectories sampled according to the trajectory distribution defined by my policy parameters phi, and inside the expectation is a reward of those trajectories. And this is also a stochastic optimization problem, right? Phi are my policy parameters in reinforcement learning. My Z's, which are my latent variables in variational autoencoders, are now my trajectories in reinforcement learning. They're also sampled under a distribution told me by phi. And the objective function F of Z is the reward of my trajectories in my long-term reinforcement learning horizon. So then the question was, why can't we do reparameterization in RL case, right? There's very close parallels between both of these classes of problems. Well, the main issue is that, first of all, Z was continuous in VAE case. My latent variables Z was continuous. In reinforcement learning, my analog was my trajectories tau. That's a sequence of discrete actions. That's one challenge. In VAEs, we saw that the distribution over Z's was reparameterizable through an epsilon vector transformed by my parameters. In reinforcement learning, my distribution over trajectories is typically not reparameterizable, right? So you can't really reparameterize it and then move the expectation, move the gradient with respect to my parameters phi inside the expectation. And finally, in VAEs, my objective function, F of Z's, was continuous and differentiable. My F of Z was the log likelihood of my data X given the Z's that I have. that's usually a decoder neural network with like a softmax or mean squared error. That's going to be continuous and differentiable. In my reinforcement learning case, my reward of my trajectories is a black box environment. Don't really know what that is. You can't backpropagate through it. So you have your states, going to this actions which define your trajectories. That's going to be discrete, and then the actions and trajectories going to the reward function is also some black box. So you don't actually know what that is. So you also can't backpropagate through that step. So that's why we looked at reinforce. Reinforce was a general purpose solution for solving these stochastic optimization problems under these constraints. But in a simpler case, and the assumptions that we have for VAE, you can solve it using reparametrization. Cool. Going to that question before, as I promised, 2 slides, we're going to see an answer to that question. One of the biggest applications of VAEs is for disentanglement. Right? We talked about latent variable models at the start. We assumed that our data distribution X was actually generated from a set of latent variables that ideally were factorized, right? My eye color, my hair color, my pose, my background, and so on. So can we actually apply VAEs to do disentanglement? And the answer is that you can, and that's perhaps one of the biggest selling points of these variational autoencoders. So essentially, disentanglement basically means that you want to learn latent variables that are independent of each other, that each are responsible for one independent factor of variation independent of the other variables. And one general recipe for disentangled representation learning using VAEs is to basically control the contributions of both objectives in my objective function. The first objective is the reconstruction objective, how well my latent variable model explains my data based on log likelihood. And the second term is how simple my latent variable model, my distribution over my latent variable Z, is to some prior in controlling simplicity. And you can actually control this with a very simple parameter beta. Higher beta, higher beta means that you care more about simplicity, you care more about the structure of your latent variables. Lower beta means you don't care that much about your structure of latent variables, and you care more about how well your latent variables explain your data. So one simple extension of VAEs is just beta VAEs. In normal VAE, we derive beta should be 1. But you can control this beta, right? Beta equals to 1 recovers VAE. Beta bigger than 1 imposes stronger constraints on these latent variables to follow some independent factorized distribution. And you're going to impose that as independent because your prior that you measure simplicity of your distribution Q with is typically some isotropic Gaussian, right? Gaussian with dimensions that don't have correlations between each other. But in general, disentanglement is a difficult problem. There's been quite a few positive results, but more recently also negative results, showing that unless you have some domain knowledge or supervision, it's going to be very, very hard to achieve disentanglement. But one good example of disentanglement, you can actually use VAEs to learn factorized multimodal representations and then do factorized generation. So over here, what I'm showing is an example. Again, I talked about this very quickly in the last lecture. If you have 2 modalities, in this case, SVHN and MNIST, 2 image modalities, you can actually learn more representations than you started with. That's representation factorization or fission, right? And the main purpose of learning more representations than you started with is that you can have one representation, ZY, measuring a joint information between both modalities. And you can also have representations ZA1 and ZA2 that are independent and uniquely define the information in each modality. So ZY tells me my digit 9, which is the shared information. ZA1 tells me the style of my first image data set, and ZA2 tells me the style of my second image data set. So given combinations of them, you can generate images through a decoder. And for ZY, which is the joint information, that should also enable you to predict the actual digit 9. So essentially, ZA1 and ZA2 learn your unimodal, and ZY learns your cross-modal interactions. And then you can start doing cool things like you can fix ZY, which is the actual joint variable telling me what digit it is. So you can generate many styles with the same digit 5 in both modalities. You can also fix the style in my first modality. So you get things on the same style, but you can vary the digits. And likewise, you can fix the style of my second modality, get the same style and vary the digits. If you don't want to do reconstruction of actual images, we've also seen that VAEs are useful for representation learning, right? We have a decoder model P of X given Z, but we also have an inference model to encode my data P of Z given X. So these folks follow up on our work. And in the case of robotics, also took in many modalities in robotics. So the robot image, that it sees the force that the robot feels and the robot state, so the particular position of its joints. Use a factorized representation to learn a disentangled representation that can be trained using self-supervised learning. So instead of actually reconstructing your data, you can also reconstruct any self-supervised signal that you wanted to learn. For example, going from action, going from what it sees to optical flow, using force data and image data to predict whether you're going to touch the object in the next time step, the 0, 1, and given a bunch of signals predicting whether it's aligned through time, so that it makes sure you learn the alignment objective. So this VAE type of model can do pretty well. It increases in performance as you have more modalities. It's able to insert this peg into the hole pretty well. There's robotics tasks. And at the same time, it's also quite robust to external forces and also occlusions, where you kind of cover the camera using some other object. So to summarize, VAs in general are relatively easy to train. We're going to see some other models that might perform better, but are much harder to train. Another good thing is that it's an explicit inference network. So not only can you generate your data, you can also take in your data and learn a distribution of my latent variables. And if your latent variables are disentangled or smaller in dimension, they can be very useful for representation learning, as we've seen in the robotics example. The biggest issue with VAEs is that they are not that good at generating high quality images. And this has to do with the fact that you're reconstructing an image. In many modalities, it's very hard to define a reconstruction objective over my high dimensional data. So VAEs tend to have more blurry images due to this reconstruction. But yes, any questions on VAEs before we move on to the next generative model? Cool. The next generative model is actually quite, many of you have probably seen this. These are autoregressive models. And autoregressive models are also a case of generative models. And the main idea in autoregressive models is that if I have some high dimensional data X that I want to model P of X, I'm going to make some factorization assumptions. I'm going to assume that I can generate my X autoregressively, 1 unit at a time. So in the case of images, instead of generating all pixels at the same time using, like, for example, MLP or using a deconvolution, I can just generate 1 pixel at a time. And if I generate pixel 1 at a time, I'm also going to make this factorization assumption that the next pixel that I generate is only going to be dependent on the previous pixels that I've already seen. Right? So essentially, you're going to learn this factorization from the time step 1 to the total number of time steps being the total number of units that I want to generate. And for each time step, I'm going to generate P of xi given I minus 1, I minus 2 all the way back to time step 1. So what it looks like is that you want to generate image, generate pixel at a time. First pixel, second pixel condition on the first, third pixel condition on second and first, and so on. This actually works really well, right? It works reasonably well. You also see in language models, autoregressive language models, where you're generating 1 word at a time, where the word that you generate at t time step depends on all the words you generated previously. And a good way of doing this is to basically have either a recurrent or a transformer architecture that takes into account the context of previous things that you generated. And likewise, you can also do this for audio. You can take it inputs, generate hierarchically 1 output, and keep the hidden states when doing this generation, and give it a new particular input, recursively or autoregressively generate the next output. Again, using the same factorization. So you've all seen autoregressive models. They're also form of generative models. But a key thing I want to talk about here is how can we actually make these autoregressive models conditional? Right? It's very easy to train just language models on language, audio models on audio, and so on. But because we're in a multimodal class, we want to learn how to condition these language models or autoregressive models better so you can do conditional generation. Right? So recall conditional generation is all about learning P of X given C, right? Not just P of X, but conditional on some variable that you want to steer your generation towards. So you want to generate images. C could be a category, like people, outdoor scenes. If you want to generate natural language, it can be unconditional, just completing natural language, or you can also use C as an image and generate a natural language description of that image. So that's also P of X given C. And sometimes you also care about style transfer, right? Given X1, so perhaps 1 sentence, and C telling me something about a style or present tense, past tense, or language, for example, can I transfer it to something else, X2, which keeps the essence of X1, but changes it just based on its style. So I'm going to cover 3 general ways of conditioning these language models, or in general, conditioning these autoregressive models, but using language as a core example of these pre-trained autoregressive models. The first one is our prefix tuning, right? So let's say I have a pre-trained language model, P of X. Typically, these are big. We don't want to change this as much as possible. This can be provided by even some black box API. So what prefix tuning does is very simple, right? Take in whatever thing that you want to condition on. So it's an image, so it's other stylistic attributes. Put that as a prefix into my language model. And the biggest issue is that this language model takes in tokens, right? It doesn't really take in images. So what you can do is you can learn an adapter that tries to map image space from image data into my text token space. And surprisingly, this actually works really well. So it's simply just taking in this image, adapting it into language token space, and still keeping the rest of the language model frozen because you don't want to change all those parameters. Gives you an adapted plus pre-trained language model. It takes into account both P of X for my pre-trained model and P of X given C because you're adapting that image into text representation space. And you can train this using small amounts of paired image and text data, right? I have the image that I want the model to be conditioned on. I have the caption that is actually conditional on the image, the small red boat on the water, and I can autoregressively predict a small red boat on the water, basically optimizing for P of X given C. It essentially learns this adaptive parameters, and that's all. You're keeping the big language model frozen. And when you test this, after training, you can give it a new image, ask a different question, what color is the car? It reliably gives you blue. So that's kind of zero-shot VQA. Zero-shot because you've not actually tested, trained it on VQA data sets, you only trained it on these kind of image and caption data sets. So you've not trained on VQA, but you can start doing VQA. You can also do outside knowledge VQA. So for example, you can give it this, doing training, give it this image of an airplane and ask who invented this as a question, and also append the answer afterwards, the Wright brothers. And give it a new question, for example, who invented this? It can also give you the right answer, Steve Jobs. So this actually relates quite a bit with reasoning, right? In reasoning, we talked about explicit knowledge. You probably need an explicit knowledge graph to solve these type of problems because most likely your training data set, especially with just one training sample, isn't going to contain an exact image and the caption that Steve Jobs invented the iPhone. But these language models, because they train a large amount of data, they contain some implicit knowledge. So instead of using explicit knowledge graphs, you can also leverage implicit knowledge from language models in this way. You can also do few-shot image classification. You can give it some nonsensical words for real-world images, and you can see whether the model learns to do the binding problem. So for this apple, you can say this is a DAX. Again, the apple goes through the fine-tune adapter. The language model is frozen. For an orange, you can say this is a Blickett. If you give it a different view of an apple, you can actually still output this is a DAX pretty reliably. So apart from images, we also show that you can do this for style transfer. So you have a particular sentence that you want to start with. For example, the market was simulated by the deal. And there's several stylistic attributes that you want to control. So maybe one stylistic attribute is this grammar. You want to change it from like passive tense to active tense. Another stylistic attribute, C2, could be intensity from 0 to 1. What you can do is that you can also encode these stylistic attributes just as these scalar variables into the input tokens, and learn an adapter to map these input tokens into your language model token space. So you can then start generating things like the deal really stimulated the market, so that changed it from passive to active tense, and also increased the intensity from just 0 to something that greatly stimulated the market. And these folks also show that it's quite compositional. So you have a bunch of independent transfer tokens, each representing a different style, C1, C2, and C3. If you train in a couple of combinations, you can also generalize the new combinations of these stylistic attributes. So that was prefix tuning. In general, a very strong method. Using the fact that you have pre-trained models, you want to freeze them so you don't have to actually backpropagate through them, and just learning some adapter layers to map any other conditional variable, like your stylistic attributes, like your image, into language model token space. Another general way is called representation tuning. So representation tuning goes a bit deeper. If just freezing your language model and adapting the inputs for a prefix isn't enough, you can also open up your language model. So these are two probably representative papers in this space. Let's say I have a pre-trained model, that's my P of X. And I say I want to condition my pre-trained language model on other modalities or conditional attribute C. What I can then do is that you can first take in all these modalities, learn an attention over them. That can tell you which modalities are important, which are important. And we know that your pre-trained language model is still going to be the most important modality, right? So I don't want to change my pre-trained language representation so much. So I'm going to have a bypass layer, like a residual layer, that keeps my language representation and only use the other conditional variables to shift my language representation. That gives me my final output as a function of the original language representation and the shifting automatically defined through the attention, the shifting given by the other modalities or other conditional attributes. So what this looks like visually is that I'm going to have these points in my representation space. The original centers are based on language model representations. And these are just shifted in some direction, a small direction based on the other modalities, just audio and visual, or shifted in other directions based on the other modalities, audio and visual. So this is also a general way to make sure that my output representations are going to depend still primarily on my language representations, but also shifted dynamically by the other modalities that you see. And the first paper here showed that this is quite useful for conditional language generation. You can have a language model, you can give stylistic attributes here, you can give an image as the other modalities as well. And given the shifted representation, you can use that to decode conditional language generation. And the second paper here showed that you can just do this for classification. So you have a pre-trained model language, that's going to do well on many tasks. But if you want to condition it on the visual and audio information at the same time in a video, you can do better video prediction than using just the language in the video. So last method is gradient tuning. So again, we're going to assume that we have a pre-trained language model as P of X. And let's say I've already generated some words like the food taste. And there's a couple of possible completions, right? And let's just say I want to condition my attribute C as sentiment, how positive or negative I feel about the food. So for some cases like terrible, that fits the completion very well. The food tastes terrible, but that's negative sentiment. The food tastes delicious is also pretty good. It completes the completion of the sentence, and it's also a positive sentiment. But you could say something like the food tastes shiny. So that doesn't really complete P of X really well, but it's still really positive sentiment when applied to other objects. So the main idea of gradient tuning in this paper and some subsequent papers is to factorize my P of X given C, which is the final language model or final model that I want to achieve, language conditional some attribute, as proportional to my P of C given X and P of X. So that's my base rule. So P of C given X, instead of actually generating data conditional on the attribute, instead classifies data to some attribute. So that's P of C given X. And P of X is just my conditional language model, unconditional language model. So ideally, if you want to maximize my P of X given C, some attribute, I want to maximize both P of C given X. So the likelihood of actually predicting the right attribute, like positive sentiment, given my completion, and also maximizing P of X. I still want my completions to be fluent, just in language model space. So visually, this looks like this from their paper. The parallel lines tell me lower P of attribute given X and higher P of attribute given X. And this blue weird shape is language model space. That tells me all regions of high likelihood just under a language model. And perhaps I started off with this initial point, which generated my completion. That's just P of X. It just from language model is very high in language model space, but it's quite low in P of C given X space, right? So what you can do is iteratively increase my P of C given X by increasing the likelihood of generating something that satisfies my attribute. So that moves it here higher into P of C given X space, but then very quickly you might leave my high P of X space, right? So you can then project it back into P of X space by taking it and increasing the directional likelihood in my language model. So you want to balance both of these objectives. And if you do that, increasing P of C given X gives you shiny and delicious. And then increasing P of X filters out the shiny and just leaves you with the word delicious as the next completion. How exactly they do this? They first take in all the input that you have, learn the final layer representation in your language model. Let's call that h of t. So these are final layer representations at time t. And my whole idea is to learn a delta ht to tell me how I should again shift my language model embedding such that ht plus delta of ht gives me a completion of the desired attribute. So the first step is to increase p of c given x. And you can do that again just using gradient ascent. The delta ht is delta ht plus some learning rate, and a gradient with respect to delta ht, the log likelihood of p predicting my correct attribute c given ht plus delta ht. So gradient ascent in the p of c given x space. And you also want to do gradient ascent in the p of x space. But typically gradient ascent in p of x space is really hard because you have to go through a whole language model. Their trick to approximate this increasing p of x is just to define a k-out divergence between my initial p of x, so initially what the language model outputs, and the new distribution of words given my new language model with this delta ht. So ideally, making sure that the changes to my language model isn't so much that it diverges too much from my original language model. And finally, I'm going to generate my next token using ht plus delta ht. So that's gradient tuning, using a separate model, p of c given x, telling me the gradients of how much I'm increasing in my c of x space, and using those gradients to update the generation from my original unconditional language model. For summary, autoregressive models are typically easy to train. They also have exact likelihood because of this factorization assumption. And the even better thing is that you don't even have to train this. Like folks have trained GPT-3 and all these image, text, audio unconditional autoregressive models for you. But the biggest difficulty is that it's typically slow to sample from, especially if you're actually doing it autoregressively. And it's also not easy to condition on. We've seen 3 examples, but it's still very hard to, for example, control like a big model like GPT-3 or other big language models using any of these current approaches. Any questions about autoregressive models? Cool. The next generative model we're going to talk about is called normalizing flows. And we've seen 2 model families so far. Autoregressive models have exact likelihood. And another big issue is that there's no way of directly computing features. There's no p of z given x. Variational autoencoders can learn feature representations. They have a p of z given x very explicitly, but they have to use approximation to estimate the intractable log likelihood. And normalizing flows is actually a way of doing both. Right? The whole idea of normalizing flows is that I have some simple distribution z that you start with, that's your prior, that's your isotropic Gaussian, and there's some very difficult distribution x that you want to model. Can I actually both have this encoder and decoder? Encoder in order to do representation learning of latent variables given data, decoder so that you can generate more data from latent variables. So the power of VAE, while also having the power of autoregressive models, which is to have an exact likelihood. And the whole idea with these normalizing flows is that if you have an invertible function that maps between my data space and latent space, then you can have both. You can have both the encoder and decoder through the function and the invertible function. And there's also a way of estimating the likelihoods exactly through these invertible functions. So how exactly do you do this? So again, looking at a simple case, just as a quick recap, because this next part requires some refresh on random variables. If x is some continuous random variable, you can define a CDF of x. So that tells me my cumulative distribution function of x bigger than or equal to a for different a in the range of x. The PDF is the gradient of this cumulative distribution function at a particular a. So again, probably some of you might recall like a Gaussian PDF is like this and a CDF is like this, goes from 0 to 1. So let's just go through some very simple examples. And again, these slides are credit to this very nice degenerative models class at Stanford. So just assume that z is a uniform random variable, uniform between 0 and 2, with some probability density function. So what is p of z of 1? So that's easy. That's just half, right? Because uniform distribution between 0 and 2 is like this. Nothing outside 0 and 2. Between 0 and 2, it has to be normalized, so it's half. Everything integrates to 1. So at any point of computing my PDF at 1, for example, that's just half. If I transform, and we're going to talk about these transformations, because the whole idea is to transform from simple distributions to more complex distributions and backwards. So if I transform my z, which is my uniform between 0 and 2, by multiplying it by 4. And let's call that x. So what's the density of x? So I multiply it by 4, that should uniformly map any point in 0 to 2 through 0 to 8, right? That's what my intuition tells me. So now I have a continuous a distribution, a PDF from 0 through 8, where again is uniform. So to make it normalized, the distribution at any point is 1/8, right? So that again integrates to 1. What if I tell you something more complex? Again, let's say z was my uniform distribution between 0 and 2, but now I transform it by taking the exponential. What is the next distribution of this exponentiated function? Anyone want to give a guess? I have a uniform 0 to 2 that's normalized with PDF 1/2, all between 0 and 2, and I start exponentiating this distribution. What's going to be a PDF? Good guess. Why?
This following the pattern.
See, it's hard, right? This is actually a really hard problem. I don't think I got this first time. So this is all about change of variables. And it's a very nice theorem. It basically says, actually gives us a nice equation for how you actually compute the new PDF of distributions under the fact that you've changed marginal distribution by some function f. So let's say z was my initial random variable. X is my new transform variable, given x equals f of z. I'm going to assume that f is monotone. So monotone means either strictly increasing or strictly decreasing. And if it's monotone, it's also going to have an inverse. Right? Z equals f inverse of x. And that's easy to see because your function is like squiggly all over the place. There's going to be 2 points in x that map to the same point in y, and you're not going to have an inverse. Then the distribution of x can be seen as distribution of z. And what z was originally is now h of x, which is the inverse, f inverse of x, with some scaled value. And the scaled value is basically the norm of the gradient of h of x, my inverse function, evaluated at x. So see how this works. So again, we had this example where z was uniform 0, 2 with a PDF 1, and I multiplied it by 4, right? So my first function from z to x is multiplying by 4. So f is multiplying by 4. My inverse function, f inverse, which is h, is a quarter, right? H of x, x over 4. Then applying this formula, p of x at some point 4 is equals to p of z, because x, you have to first transform x to z, right? So 4 becomes 4 divided by 4 equals to 1. So basically computing my point x, what z originally was. So p of z of 1. And then plugging into this equation, the gradient of h, my inverse function, at the point x, so 4. And h was x over 4. H prime, my gradient is just a quarter. With a norm, so that's half times a quarter, it becomes 1/8. Right? So that's worked for the simple case. Let's look at the exponentiated case. Z was my initial random variable. F is my exponentiation function. H of x is the inverse of exponentiation, is the natural log function, natural log of x. So P of x is equal to P of z, applying the inverse transformation to bring x back to z. So that's natural log of x. Now, the norm of the gradient of h, the inverse function evaluated at x. So gradient of log is 1 over x, and P of z log x is just half. So that gives you 1 over 2x. And you just got to change the range, right? The range of exponential 0 to 2 now becomes the range of exponential of 2 and exponential of 0 and exponential of 2. So that's like this. You're going to have a PDF and raised to 1. The range from exponential 0 to exponential of 2. It starts at half, and the function is 1 over 2x. It starts going down like this. So following this equation, you can actually see that the shape, right? It used to be uniform and nice block. Some transformations preserve the shape, some transformations that are still invertible, and you can still compute the likelihood exactly. It's going to start changing the shape. It's going to be a bit more complex. And you can start thinking, if you have a bunch of compositional transformations, you can start from a simple distribution and eventually go more and more complex. So very quickly, the high dimensional case, that was one dimension. So again, let's say z was some vector in 0 by 1, 0 by 1. And I'm going to assume that I can also start transforming this vector z. So x equals to a times z for some square invertible matrix A. And because it's invertible, let's assume the inverse is w. So what does x look like? So let's just say My initial Z was just a box, uniform 0, 1, 0, 1. That's a square. I'm going to transform it by matrix A. That's going to stretch my box into some parallelogram with given endpoints. In a uniform case, we know that whatever was uniform is now still uniform. But now my uniform has to be divided by my area, right? Because it has to normalize to 1. And the area of this parallelogram is actually given very nicely by the determinant function. There's a nice proof of this given here. So now my new distribution, x, is equal to P of Z. So whatever x was, that's applying the inverse function W to x, that's A inverse x, is divided by the new area of my parallelogram. And the area of parallelogram is given by the determinant of A, which is the inverse function. And that's equals to actually multiplying by the determinant of W, which is the inverse function. Right? Because if W is A inverse, the determinant is also of W is 1 over the determinant of A. And notice similarly the 1D case, right? So my P of x is going to equal to P of Z, whatever inverse function that transforms x back into Z space, and the norm of my gradient of my inverse function. It just happens that the gradient of the inverse function in this case is just a matrix A because it's a linear function. So for linear transformations, it's all about first looking at, given my new Z that you transform into, what my previous function in X was. So apply my inverse function in Z. And you also got to stretch it by the change in volume. That was the second term in the equation, right? And over here, the stretch in my volume, it was determinant of A, my inverse, my original mapping. So the change in volume is given by the determinant of my matrix A. In the more general nonlinear case, the change in volume is given by the determinant of the Jacobian. And Jacobian is basically the gradient function in one dimension extended to multiple dimensions. So my f is an n by n function that takes in vectors n, outputs vectors n. My Jacobian is going to be this gradient matrix as n by n, right? Every single entry of the output with respect to every single entry of the input. That's n by n Jacobian matrix. And that gives us our change of variables in a more general case. If I have an input x, I have a revertible function f that's mapping n to n. Again, invertible functions have to have the same input and output dimension, or it's not going to be invertible. So if I have z and I can map it to x given this invertible function, and there's some f inverse is the inverse, then my p of x is going to by p of z. Whatever z is going to be equal to f inverse x, and you also got to multiply by the change in volume, the determinant of my Jacobian of the inverse function, f inverse x over x. So several notes. It first generalizes the 1D case, right? Gradients of my one-dimensional function become, again, a higher order gradient given by my Jacobian. Norm in one-dimensional case becomes norm of determinant in the higher order case. Another big note, unlike VAEs, all my intermediate representations x and z have to be continuous. And another big constraint is that they have to have the same dimension, because once you start having different dimensions between x and z, you cannot define an invertible function. And finally, it's just the property that determinant A inverse determinant A, computing that and then doing 1 over that, so you can pull the inverse outside of it. And that gives us a general recipe for computing normalizing flows. If I have a simple distribution z, I want to go to a complex distribution x, can I define an invertible function? X is f of z, and therefore z is f inverse of x. And if I can do that, then I can start doing exact max likelihood estimation. The log likelihood of my data is going to be exactly equal to the log likelihood in my z space. So p of z, f inverse x, plus this determinant function. Yes, strictly, but there's some optimization that you can do, like first encoding data into some space, and then operating within that space. So kind of combining both the exact log likelihood based on invertible transformations and maybe some approximate inference at the beginning. But as you mentioned, yes, I'm gonna get to that. That's one big issue of normalizing flows, is that the architecture that you can start working with is going to be quite constrained. It has to be these invertible transformations. So you compute max likelihood exactly because it's going to be invertible. And once you're done maximizing log likelihood, you can also do sampling and inference very quickly. Sampling is all about taking x and applying a function f into z space, and inverse, which is inference, which is taking x up, getting into z space that allows you to extract features, and sampling is all about taking these data variables z and applying the inverse function back in the data space. Well, I'm not up to date with the most recent work, but at least in the original definition, it has to be f and f inverse. So once you define one function, the other function is automatically determined for you, right? So if you use different functions, then you probably won't be able to compute the exact likelihood because f and f inverse won't be actually inverses of each other. And if you think, and again, there's many questions about the constraints of this model. If you think that one function f, one invertible function f, isn't enough to get you to very simple latent space in the data space, you can also compose multiple invertible transformations. We saw in the previous case, we are uniform, and exponentiate it, become a curve. So that's just one step, but you can do it across multiple steps. And the hope is that if you do this across multiple steps, you're slowly going to start from a simple Gaussian distribution, a simple uniform distribution, and eventually get more and more complex distributions that more closely resemble your actual data. And you can actually do this, right? You can first define your prior, Z0. You can define a sequence of invertible transformations, F1 all the way through Fk, that gets you your Z1s through Zks, and finally gets you your X. And for your inference, you can apply the invertible transformations one by one. So again, going from Z to X is your functions F1 through Fk, and your inverse transformations from data, you can apply Fk inverse, Fk minus 1 inverse, slowly back to F1 inverse. And your density is still well defined, right? The density just recursively accumulates P of Z1 as a function of P of Zi minus 1. So P of Zi is a function of P of Zi minus 1 scaled by this determinant of your Jacobian matrix. And in the end, you can still exactly maximize the data log likelihood. Instead of just one volume determinant function, you have a sum over all steps in your invertible function. So you can still exactly compute your log likelihood with layers of inverse functions. And there's some general tips, right? You first want to start with a simple prior, for example, isotropic Gaussian. The biggest issue is that you got to define these invertible functions. And also, if you want to define invertible transformations where you can actually compute a Jacobian pretty easily. So in general, for dense invertible matrices, computing a Jacobian and determinants takes n cube time. To be precise, determinants take n cube time. But what you can do is you can choose a very specific type of invertible transformation, a triangular matrix. So your triangular matrix, the determinant is basically 1 over each of the triangular and the diagonal entries in your matrix. So that becomes O of variational n cube. So some tricks. Again, please refer to this nice course on deep generative models for more details. And just to give one example of these in practice, this was probably one of the very popular normalizing flows models that generated these faces with high accuracy, high fidelity. And they basically compose invertible functions like this. Act norm, invertible 1-by-1 convolution, affine coupling layer. And again, there was this table in the paper for each of these operations, act norm, invertible convolution, affine coupling, the function, the forward function, and also the inverse function. So you gotta be able to compute the inverse. And if you have the forward function and the inverse function, you can compute the log determinant. And that was the scaling factor that we have. And once you had all these in place, you could do exact likelihood computation of your data. So computing the exact log likelihood. So yeah, normalizing flows. It's quite easy to train. Exact likelihood is a big plus. But the biggest issue is that you have a pretty constrained architecture. And it shouldn't be surprising that there's a bunch of work combining the 3 models that we've seen so far. VAEs, autoregressive models, normalizing flows. Each with their pros and cons. There's autoregressive flows. And there's also ways to combine VAEs with flows to perhaps relax the invertible assumption and do both exact inference for invertible parts and approximate inference for non-invertible parts. So check out this blog post for more examples. Cool. So in the last 10 minutes, I'm going to talk about GANs. And next lecture, we're going to talk about the very last example of generative models called diffusion models, which are all the rage nowadays. But quickly about GANs. So GANs deviate from previous methods. All the methods we've seen are all likelihood-based, right? This is P of X that you want to estimate. You can estimate exactly using autoregressive models or normalizing flows. You can do approximate inference using VAEs. GANs deviate from this by doing likelihood-free based learning, likelihood-free learning. And the main idea is that it's going to be hard to optimize P of X, no matter exact or approximate inference. And even if we do estimate P of X exactly, it may not correspond to high-density samples. So the key idea is that instead of doing likelihood-based, I'm not going to use any likelihoods. I'm just going to work in sample space. If I have a bunch of samples that are real and a bunch of samples that my model generates, how can I distinguish between these two sample distributions? And the whole idea of GANs is exactly based on these two sample tests. Going from one set of data, S1, samples from one distribution P, and S2 is samples from one distribution Q. A two sample test basically tests null hypothesis that P and Q are actually the same distribution from which we see these samples, versus the fact that P and Q are different distributions that actually generated these two samples. The key idea is that this test statistic, which basically computes a difference between the samples, is likelihood-free, because you're not going to compute the estimates of P of X. All you're going to do is to operate in differences in sample space. But this two sample test is very difficult. Right? We don't actually know how to have these two sample tests in high dimensions. So instead of actually defining a fixed two sample test, can also train a model. Can also train a model to recover, can actually train a model to actually mimic this two sample test. A model that basically distinguishes between samples that are from the same distribution and samples that are from different distributions. And that's the whole idea of GANs, right? I'm going to first have a generator that takes in the latent variable Z and generates data X with some parameters data. The goal of this generator is to minimize the two sample tests. So you want to make sure that the data that you generate is the same as the actual data distribution. That the actual data distribution is the same as the actual data that you generate. And a discriminator is trying to distinguish between the actual data distribution and the samples that you generate. So it's going to do the opposite thing. It's going to try to maximize the two sample tests to support the alternative hypothesis. The actual data distribution is not the same as the data distribution that you generate. So both of these generators and discriminators are going to optimize the same objective, just inverse of each other. What a discriminator starts to do is to maximize over discriminator parameters. A value function is a function of both generator and discriminator. The cross entropy, the binary cross entropy loss, that increases the likelihood of identifying data from the true data distribution. That's my first term. And decreasing the likelihood of assigning real to the data actually generated by the discriminator. And basically a binary cross entropy loss. And you can actually show that the optimal discriminator, when you start learning this, is going to be a likelihood ratio of the density P of X assigned to my actual data over the total P of X, the actual data and the generated data. The generator is going to do the opposite. I'm going to try to minimize this objective. So I'm going to say against the discriminator. Again, what a discriminator has, which was to binary cross entropy distinguish between real and positive samples, the generator is going to minimize that objective. And for the actual optimal discriminator, which we have from this previous slide, the fact the optimal discriminator assigns likelihood, gives you a likelihood ratio between the data distribution from the real one over the total likelihood. If you plug this into the generated distribution, you're actually going to obtain something that minimizes some other divergence between the real data and the generated data. So basically, you can actually prove that a generator actually manages to minimize a Jensen-Shannon divergence between the actual data and the generated data, where the Jensen-Shannon divergence is simply a symmetric version of the KR divergence that we've seen previously. So ideally, if you train the generator to completion, the generated data distribution should be equal to the real data distribution. But because this is a discriminator that's playing against the generator, you're not going to be able to achieve the exact equality in generated and true data distribution. So very quickly for GANs, you're going to first sample a mini batch of training points. That's from the true data distribution. You're going to sample a bunch of noise vectors Z, and you're going to play the generator and discriminator against each other. For the generator parameters, I'm going to optimize using stochastic gradient descent against the discriminator. So that's how well I fool the discriminator into actually distinguishing, not being able to distinguish real data from generated data. And for my discriminator parameters, I'm going to try to optimize this cross entropy loss that actually classifies real data as real and fake data as fake. I'm going to repeat this a bunch of times. And typically these GANs, as you might see, they're quite hard to train You gotta do this iteratively. You gotta fix the generator, update the discriminator. You gotta fix the discriminator, update the generator. And typically users see some collapse. The discriminator has a much easier job to play in GANs than a generator. So you can have a very good discriminator that very easily discriminates real or fake while still not having trained a very good generator. There's some optimizations. I'm not going to go into more details. Again, check the degenerative models class for more details. But essentially, you're seeing quite a few examples of generative models, right? There's likelihood based on VAEs. You approximately optimize the evidence lower bound. You've seen autoregressive models. You can do exact inference via chain rule by decoupling generation at each particular step. We also see normalizing flows, which can do exact inference via invertible transformations. And for likelihood free, we've seen GANs, there's a bunch of work in GANs, but the main idea is to discriminate between real and fake samples instead of going into likelihood space. And there's pros and cons of each. VAEs are really fast and easy to train. You can also do inference of latent variables given data. The biggest issue is that they generate data of lower quality. For autoregressive models, they're also easy to train. You have exact likelihood, but typically they're slow to sample from because you got to do it autoregressively. And also it's really hard to condition them. For flows, it's easy to train with exact likelihood, but you have a very constrained architecture. And for GANs, you get much higher generation quality because you're not relying on any reconstruction or likelihood based. You're trying to distinguish between real and fake samples. So you can, if you train them well, get really high quality samples, but it's usually much harder to train. Another big issue is that GAN is just a single direction from latent variables to my data X. You can't really do the inverse direction of getting latent variables from your data unless you do some other extensions. And finally, we're going to talk about diffusion models really quickly next lecture. And then we're going to move on to the next challenge on transference. Cool. Thanks, everyone. And any last questions about GANs or any generative models? I'm not an expert, so I don't think I have any opinions to give, but it seems like a promising field of research.